In the previous lecture, we saw a relationship among the shear force and the bending moment in a beam. When we talked about equilibrium of beams, there was a derivative and integral relationship between those two quantities. In this lecture, we're going to formally see where that relationship comes from, and also see that the load on a beam factors into that as well. So what I have sketched here is a section of a beam with an arbitrary distributed load on it. The load is pointed upward in the positive direction for the y-axis, and the load is denoted P of x, indicating that it changes with x, and it's a force per length along the beam. On the left-hand side, my coordinate system starts somewhere. I get to my first location here at position x. Right here is position x. And a little bit further down the length of the beam, I've also indicated another little red squiggle here at position x plus delta x. Now this diagram that I have is not a Freebody diagram, but I'm going to take a Freebody diagram out of this beam schematic and sketch that. So I'm going to indicate the cut for the Freebody diagram with these kind of squiggly lines. And then the top and bottom surface of the beam by these blue lines. And on this I have the section of this distributed load. Maybe it does something like this. And I'll indicate the load over here. And I'm going to draw in my shear force and my bending moment in their positive directions. Positive shear force goes down on the right side. Positive bending moment puts the top of the beam in compression. And then positive bending moment on the left-hand side and a shear force on the left-hand side going up for positive. Remember, these are internal shear force and bending moments, and we have a very definite sign convention for these quantities. Now the left side of this Freebody diagram is at position x. So to make that very clear, I'm going to put V of x and M of x and even P of x over here on the left-hand side. And over on the right-hand side, we go a length of the beam a little bit further down, a distance delta x. Now we're at position x plus delta x. So to make that explicitly clear, I will indicate that notation on this side as well. And so the entire length of the distributed load on the right-hand side is P of x plus delta x. Now to show this relationship among the load, the shear force, and the bending moments, what we're going to do is the summation of forces and the summation of moments for this free body diagram. Before we get started though, I want to label a point. I'm going to call this cut point over here on the right point O. And I'm going to do the summation of moments about that point in just a moment. Before we do that though, let's make a little room. We'll scoot this free body diagram segment upward, and then we'll have enough room to do the summation of forces in the y direction. Okay, so there's my free body diagram, and we're going to take a look first at the relationship between the load and the shear force on the beam. So to do this, I'm going to do the summation of forces in the y direction. And to help me a little bit with this distributed load, I'm going to break this distributed load up into a constant part so that it is the same height all the way across of P of x. And then over on the right hand side, it's a little bit higher than P of x. I'm going to call that extra distance right here delta P. So we'll deal with that in just a moment. Let's do the summation of forces in the y direction. On the left hand side, I have V of x pointed upward. On the right hand side, I have V of x plus delta x pointed downward, so negative. And then my force is going to be upward. I have the constant distributed load portion P of x times delta x. And then I have some extra force. And exactly where it is, I can't really tell you for sure exactly what that amount is unless I know the shape of this region that lies above the rectangle that I just drew. So what I'm going to do is I'm going to say that it's upward, and it depends on delta P and delta X, and then if I knew the exact shape, then I could put a constant here called a shaping constant that would help me figure out what that area is. We're going to see that that term drops out in a moment. So let's just write this down. C1 is a shaping constant. So for example, C1 is equal to 0 if P of X is constant. If we have a triangular distributed load, then C1 would be equal to 1/2. And for any shape, we could find out that it's some constant times delta P and delta X. Alright, so let's do our summation of forces by and rearrange these terms right here. I want to lead off with V of X plus delta X is positive, so let's do that. I'm going to put all the V terms on one side, and I'm going to put everything else on the other side. Right, so that would be P of X times delta X, and then plus the shaping constant times delta P and delta X. I'm going to take and I'm going to divide through both sides of this equation by delta X. And then we've done something like this a few times already. I'm going to take the limit as delta X goes to 0 for both sides of this equation. And in the limit as delta X goes to 0, what we have then is the definition of a derivative. So this is the derivative of the shear force with respect to X. And on the right hand side, we have P of X, and we have to deal with this. Now if we shrink delta X down to 0, I think you can see that in the limit, the delta P term will go to 0. So that term will drop out. So what it says then is if we knew the shear force equation in the beam, if we could take the derivative of it, we would find the distributed load equation for the beam. We usually know things the other way around though. We start off knowing what the distributed load equation for the beam would be. Triangular distributed load, that's linear in X, constant distributed load, something like that. And we want to find out what the shear force is in the beam. In that case, we would integrate both sides. So if we do that, the change in the shear force would be equal to an integral along the length of the beam of P of X dx. Or if we want to do this in terms of an indefinite integral, the shear force equation in the beam is going to be equal to an integral of P of X dx plus a constant of integration. And just to not confuse this constant of integration with what we used as a shaping constant, I'll just call that a different term, some kind of constant 1. This will be the basis for our graphical integration when we go to do that in just a few moments. Before we do that though, let's go ahead and find our relationship between the shear force, the internal shear force, and the internal moment for a beam. To do that, we're going to do the summation of moments about that spot O. And in this case, if I take this direction as positive, I'll have m of x plus delta x minus m of x from the left-hand side, going the negative sense of rotation. The v of x plus delta x has a 0 moment arm, but I have a minus shear force on the left-hand side, v of x, times the moment arm distance of delta x. Now I also have a contribution to the moment from the distributed load, we will see that that drops out, but we're going to put this in here for now. Acting in the negative sense of rotation, I have the statically equivalent force from the constant portion of the distributed load times its moment arm distance. And again, there will be an equivalent load from everything that's above the constant distributed portion P of x times a moment arm distance. And I'm going to treat that in a very similar way. I'm going to write this down on the next line as a minus some other shaping constant C2 times delta P times delta x squared, and the equal to 0 for equilibrium. And the shaping constant C2 depends on the exact shape. We'll get a certain value if it's a triangular distributed load and so forth. So I'm just going to label this as another shape constant. Alright, we're going to do the same thing. We're going to put all of our m terms on one side. I'm going to put everything else on the right-hand side. And I'm just going to go ahead and, at this step, also divide through both terms by delta x, in which case I have positive v of x, and then I have a plus p of x times a delta x over 2, and I have a plus c2 delta p times delta x, and I will take the limit of both sides as delta x goes to 0. Again, we have a derivative relationship. The derivative of the moment with respect to x is equal to v of x, and it's more clear to see maybe in this case that delta x goes away. These terms go away because delta x approaches 0 in the limit. And so again, if we know what the moment equation is in the beam, we can take a derivative of that with respect to x and find out what the shear force is in the beam. Or again, we're more likely to approach it the other way. We would know what the shear force equation in the beam is, and we would want to find what our moment equation is by doing an integral. And if we do an indefinite integral, we have v of x integrated with respect to x plus some other constant of integration. Now, not all relationships between the load, the force, and the moment are smooth functional relationships. We can have discontinuities or jumps. If you might remember from statics, that if you have a concentrated force or a concentrated moment, there will be an upward or downward movement of your shear force or bending moment diagram. And so concentrated forces and moments cause these jumps in the equations. So let me draw a little section of a beam. And this is not a Freebody diagram, this is just a schematic. Suppose I have a force that's applied to this beam of P0. And I have, here's my shear force on the right, and here's my shear force on the left. As I go from left to right in my beam, I will have a downward jump in my shear force diagram since the load is directed downward. As we approach from the left and go to the right, we have this discontinuity, and then it continues on. This position, the shear force is VL. This jump is value P0, and this value down here would be the shear force on the right. Now it's pretty easy if you have a concentrated force because your shear force diagram just goes in the direction of that applied load. If my applied load is directed upward, I have an increase in my shear, internal shear in my beam as I travel from the left to the right. A little bit harder sometimes to remember what happens is if we have a concentrated moment applied to our beam. Let's draw this diagram. Right. Suppose I have a point there and I have a moment applied to my beam. I'm just going to put this moment this way. I'm going to call that M0. And important to this diagram is to put my moment on the right and my moment on the left in their positive directions. maybe we'll call this point O. And I need to know whether or not that causes a jump upward in my moment diagram or a downward jump in my moment diagram. This is probably one of the most complicated things for students to understand. Well, let me take that back. I shouldn't say that it's complicated for students to understand, but it is something that I often see students mess up with. Here's a surefire way to know whether or not this applied bending moment in that direction causes an increase or decrease in my internal bending moment. I'm going to do the summation of moments about point O. Doesn't matter which way I call positive in this moment equation. It's going to be set equal to 0 for equilibrium. But I'm going to have my moment on the right, that's in the positive direction. The moment on the left is in the negative direction. And as I have applied this moment in this way, let's see, what is that? That's clockwise. That goes in my negative sense of rotation right there. Okay, equal to 0 for equilibrium. All right, now I'm going to do something. I'm going to solve for the moment on the right-hand side. The moment on the right-hand side is going to be equal to taking these two terms over to the other side of the equal sign, the moment on the left plus the applied moment. What that means is when I have my moment diagram and I'm moving from my left and I have the moment on the left as a certain value, when I hit the applied moment in this clockwise direction, it jumps up by the value of m0, and it continues on with the value mr until something else happens. Okay, so if you like to memorize things, I guess you can memorize that a clockwise applied moment causes an increase in your moment diagram. But I can tell you from my experience, I try to memorize as little as I need to. If I understand how to do equilibrium, and everybody's done that a million times by now, then it's pretty easy to draw this little free body diagram and you can figure out whether or not your internal bending moment increases or decreases just by making that sketch. Alright, so that's what we can do with concentrated forces or moments. So with that background, we're ready to start talking about shear force and moment diagrams. We're interested in finding shear force and moment diagrams because it'll be easy for us to pick out the critical locations on the beam where the stresses are the highest, because those usually occur where the internal shearing force and internal bending moment are the highest in those beams. There are three basic ways to sketch shear force and bending moment diagrams. We're going to start off with a couple methods and then we'll make them, we'll go to some, probably my preferred method at the end of these three methods. Now the first method is what I'll call the equation method or the direct integration method. And in this case, we want to find the distributed load equation of the beam, and we want to apply those rules that we just saw to integrate it once for the shear force and integrate that resulting equation to get the bending moment for the beam, and then make a plot. So let's just kind of outline this. So we find our P of X, integrate once for V, and again for M. So let's do an example. Suppose we have a beam that has a wall on the right hand side. I'm going to try to make this a little bit easy for me this way. And I have a triangular distributed load, and it's of height P0 over at the wall, and this load points downward. And our coordinate system starts here and goes to the right. The length of my beam is L. Well, I need to find the equation for this distributed load. Now it's an equation of a line, and so that equation of a line is like y is equal to mx plus b, but we're taking a look at finding the load function p of x. So we have p of x, or p, is equal to mx plus b. Let's just put the p of x right there. In order to find the slope and the intercept for this equation of the line, we need to know the values of the distributed load at two spots on our beam. On the left-hand side, where x is equal to 0, the distributed load is equal to 0. And over on the right-hand side, at x equal to L, the value of the distributed load is minus p naught. Because it's directed downward, that's why there's a minus sign right here. So knowing those 2 points, I can put in x equal to 0 and p is equal to 0. This one will tell me that my intercept is equal to 0, and that makes sense since that's what it looks like based on this picture. And once I know my intercept is 0, I can find that minus p naught is equal to the slope times the x distance plus my intercept, so my slope is going to be equal to minus p naught over L. So this means that my p of x equation is equal to minus p naught over L times x. Well, knowing that v of x is equal to the integral of p of x dx plus a constant of integration, call that C1 now, I can put that in here, and I'm left with integrating minus p naught over L times x dx. And I get, let's see, I add 1 to the exponent, and I divide by the new exponent, and then I have this constant of integration. Now the constant of integration in this case depends on the boundary condition on shear force for this beam. If we look at this beam at position x equal to 0, there is no shear force. So if we plug these conditions in, we will find out that C1 is equal to 0. It's not always going to be 0. If you have an applied force on the tip of the beam directed downward, then your internal shearing force will be affected by that downward directed force at the end of the beam. I also want to mention that you have to do these equations such that they're continuous from one section of the beam to the other. So what I mean by that is from start to finish, from 0 to L, I have one continuous equation. If I have applied forces in between, if my distributed load function changes to a constant distributed load, I'll have to use more than one distributed load equation and enforce continuity equations in these sections. So this integration method isn't necessarily the easiest for all cases, but in some cases it's pretty straightforward, like in this case. Now if I want to find the moment as a function of position x, well then we know that that's the integral of the shear force with respect to x plus another constant of integration. In this case, if I integrate a quadratic, I will get a cubic. I add 1 to the exponent, divide by the new exponent, and since I knew that C1 was 0, I don't have that anymore, but I could have a second constant of integration. But once again, I do not have any moment condition at x equal to 0, so at x equal to 0, the internal moment is equal to 0. And again, it's important to know that these are the internal moments and not applied moments at the end. They might be the same value, but they could have different signs. But this case, this condition gives us C2 is equal to 0. So now I know what my two equations are. Let me write them over here to the right. I have an equation for v of x, and I have an equation for m of x. One is a quadratic and the other is a cubic equation. So now that I have these equations, I can go and make a plot. Let's do that on the next page. Okay, so let's see if I have if I want to plot my internal shearing force with respect to x, then as I increase from 0 to L, I have a quadratic relationship. The curves down. And at the end of the beam, I'm down here, and the value of this point is going to be equal to minus P naught over L times L squared over 2 is equal to minus P naught L over 2. If I were to plot my moment equation, it's a cubic equation with x. Maybe it does something like that. And my quadratics and cubics, okay, they look pretty similar, so I'm just going to make a little note. This is a third order equation, and this is a second order equation. But the value over here on the right hand side is minus P naught over L times L cubed over 6, which is going to be minus P naught L squared over 6. Let's take a look at our free body diagram and see how that relates to the reactions of our beam. Okay, so it's a cantilevered beam, and let's draw the external reaction this way. Call that MW, and let's draw the force reaction going up this way. Let's call that VW for the moment reaction at the wall and the shear force reaction at the wall. Now I have this triangular distributed load, and the statically equivalent force from that is 1/2 P naught times L directed downward. So when I do my summation of forces in the y direction, I have 1/2 P naught L going down plus V at the wall equal to 0. The shear force at the wall is equal to 1/2 P naught L. And likewise, if I do my summation of moments, let's see, at the wall, go that way positive, I'll have minus MW minus the force times the moment arm distance. And I can solve for the moment at the wall, the moment reaction, as minus 1/6 P naught L squared. Now, I want us to pay attention to something about these reactions. And let's circle these reactions in red, so keep in mind what we're talking about. And before I do that, I need to fix one thing. This actually should have been positive, which makes this term positive. So I did my summation of moments in this way positive. Okay, something we need to talk about with these external reactions. And let me label these. The external reactions are not necessarily the value of the internal shearing force and bending moment. They will only be the value of the internal shearing force and bending moment if you draw them according to the positive sign convention for the internal shearing force and bending moment. They'll have the same magnitudes, sure, but they may not have the right sign unless you set these reactions up to have the appropriate signs to make everything work out. Now, oftentimes you'll hear people say that the shear force and bending moment diagrams will close back to 0. Well, that's not really true. If you're at the end of the beam, you're at the end of the beam. If we look at this, the shear force is going upward. That means we have a negative internal shearing force at the end of the beam. That's why the shear force diagram goes to minus P naught L over 2. And at the end of the beam, we have this bending moment reaction of positive 1/6 P naught L squared, but that is putting the top of the beam in tension, Well, that corresponds to a negative internal bending moment. That's why this internal bending moment equation ends at minus P naught L squared over 6. Alright, so I just want to make that clear. They don't necessarily have to close, but they need to end at the values, the magnitudes of the reactions. Okay, we're going to take a look at a couple more methods to find internal shearing force and bending moment diagrams. In this next method I call the equilibrium method. We alluded to this at the end of the last lecture, where if we had maybe a beam, let's draw the simplest supported beam with a couple of different loads on it. Maybe here's a W naught and here's another load. Maybe this is 2W naught. If we have our coordinate system starting on the left hand side going to the right, we can make a cut inside section 1 and find our internal shearing force and our bending moment as a function of position X. And then we can cut inside region 2 and find our internal shearing force V2 and our internal bending moment M2 as a function of position X in that region. And then we can plot. So we just do this directly by statics or by equilibrium methods. Now the equations that we would get are just the same as what we had previously if we have one region. But if we have multiple regions, then this might be another way that we can approach that. Now the third method that we're going to show then, and the one that I really recommend, particularly for my exam 2, is the graphical method. And that's where we use graphical integration to sketch our shear force and bending moment diagrams. Right, so I'll go through an example of doing that, and it's something that you should have done or would have done in statics, the prerequisite to this course, but it's always good to see another approach. Maybe you pick up a couple tips on how to do this. So to illustrate the graphical approach to integration for shear force and bending moment diagrams, let's take a look at this example. I have a pin connection on the left side of my beam, and I have a roller 4 meters away from it. In between the pin and the roller is 4 meters, and I have 8 kilonewton per meter distributed load applied to the beam as a constant distributed load. And on the very end of the beam I have a 2 meter overhang with a 16 kilonewton force directed downward that's applied to it. Now I've gone ahead and drawn the Freebody diagram, and I've written down the reactions so that we can get right to the shear force diagram. I have an 8 kilonewton reaction going up at the pin, and at the roller I have 40 kilonewtons directed upward. So we're going to start off on the right hand panel of this screen. We're going to start off with our shear force diagram. Now I'm going to label this V, that's my internal shearing force diagram, and I'm going to put my units on these axes. And I think that this is so important that these axes get labeled with units that I will look for them on a test. And if you don't have the proper units here, I will take some points off, because we need to know if we're working with newtons or kilonewtons or feet and pounds, pound feet, kip feet, whatever our units are. In order to calculate the stresses from these internal shearing forces and bending moments, we need to know what units we're working with. That's why we'll look for that. Okay, we're going to start from the left-hand side and work our way to the right. And we know that an applied force, a concentrated force directed upward, causes an immediate upward increase in our shear diagram. So it's going to move this to 8 units immediately. Here is an 8 kilonewton per meter distributed load. That's a constant distributed load. I know that the shear force is the integral of the distributed load. When I integrate something that's a constant, I get something first order in x. It's going to be a line. It's going to be a straight line. This force is directed downward. It has an area of this distribution of 8 by 4 of 32 kilonewtons. That means that I am going to take this, 8 times 4 is 36. Well, hang on. Let me say that right. 8 times 4 is 32. It has an area of 32 units. That's going to cause a decrease in my shear force of 32 units. So that means I'm going to be down here at minus 24 units after I go a distance of 4 meters. Okay, so this total drop is 32. It goes by a straight sloping downward line because this is a constant distributed load directed downward. Once I hit the roller, I jump upward by 40 units. But I'm down here at minus 24. Okay, so this whole thing is 40 units. That puts me at plus 16. And there's nothing happening in between the end of this load and this roller and the end of the beam. So it just comes along, and there I have 16 kilonewtons, which is a positive internal shearing force. So I stop at 16. Alright, now I'm going to draw my moment diagram. And my units for my moment diagram are kilonewton meters on the vertical axis and meters for the horizontal axis. My beam does not have any applied moment on it, so my internal bending moment is going to be 0 to begin with. I also know it's going to end up being 0 over here because, again, there's no applied moment on the end of this beam. Now, the first thing I get to in this picture is this triangle. This triangle is up, so I'm going to have an increase in my bending moment. Since this is a linear equation, I'm going to increase like a quadratic. Now I have a choice when I draw my quadratic. I can draw it like the solid line and have it curved that way, or I can draw the quadratic where it comes and opens this way, like an opening parabola. I can show you how to figure out which case that's going to be. And the way to do that is, let me use a different color. If we look at a little strip of this triangle on the left-hand side, and a little strip of the same width on the right-hand side, notice how much more area there is over here on the left-hand side than there is on the right. That means that this parabola increases very sharply at first, and then it tends to slow down. Now, if I know the area of this triangle, I can find the value for that internal bending moment. Well, if I know the distance, I'll call this distance d, then the area of this is going to be 1/2 the base times the height. I need to find that distance d. There's a couple ways we can do it. Easiest way, I think, well, in this case, an easy way to do it is with similar triangles. If we look at the big triangle that goes from plus 8 down to minus 24, and over here, the sides of that triangle are in the proportion of 32 to 4. And that's going to have the same proportions as the smaller triangle that has dimensions of 8 by d. There's our similar triangles again. So if I cross multiply, I can find that d is going to end up being 1 meter. So if d is equal to 1 meter, let's see, 8 times 1 is 8 divided by 2. I'm going to be here at 4 kilonewton meters for this point right here. And again, it curves that way. On the other side of that 0 point, I have a area that's below the x-axis. It's going to cause a decrease in my internal bending moment. If I know that this is 1 meter, then because the whole distance is 4 meters, I know this is 3, and the area of this triangle is going to be 1/2 the base times the height, which is 24. Let's see, that's going to be 36. So I'm going to decrease by 36 since this area is down here. So I'm at 4. Now I'm going to go and decrease down to minus 32. By the same reasoning that as I found the curvature of the parabola, I can do this on this triangle as well. See, there's a little bit of area here and there's a whole lot of area there. That means that this parabola, once it gets flat, it starts to change slowly and then it starts to speed up and have that shape. Now, if you're really good and remember things from calculus like concave up and concave down and different convexities, there's a special name for this. I always forget what it is. I rely on being able to figure out the curvature of that parabola, the concavity, based on what that picture looks like. And it's pretty easy to do. And I want to point out that if we had a triangular distributed load, you could do this to find the concavity of the shear force. You can even do this sort of approach if you had a parabolic curve and you want to put a cubic moment equation and sketch it out. Same sort of approach is valid in there as well. Alright, so it goes in this curvature. The last bit here is a constant a constant shear force. The area of this is 16 by 2. The area of that is 32, and this area is above the x-axis, so we have an increase in our bending moment. Because this is a constant shear force, when we integrate that with respect to x, we get something linear for our bending moment equation. We get a straight line that slopes upward from minus 32. It goes up by 32, and we do end up at 0. Now, I knew we had to end up at 0 because we didn't have a moment over here. If for some reason I had a value that was not 0, I probably made some kind of algebra mistake somewhere. Alright, so go back and look for it. Now, it doesn't have to end at 0. Your diagrams don't have to end at 0, but they should end at the magnitude of the reaction. And if you count for the sign of the internal shearing force and bending moment, they should end at that value of the internal shearing force and bending moment. Okay, so this is an example of the graphical integration method. So the homework that you'll have associated with these types of problems will be a few sketches. Find your reactions using statics and go through. Be careful about any concentrated forces and moments. We talked about how those jump up or down, and we showed how you can figure out if it jumps up or down, and then sketch these diagrams.